So what have we learned? First of all, we've learned to write physical relationships using tensors. This is because tensors have some kind of physical meaning beyond the coordinate system we choose. And of course, there's no reason for the universe to respect our choice of coordinate system. So we talk about electromagnetic fields explicitly in terms of tensors, rank 2 tensors in that case. We talk about 4 vectors and 4 currents rather than 3 vectors and 3 currents because it's 4 vectors and 4 tensors that obey Lorenz invariance. In other words, they're the things that are compatible with special relativity. We have Maxwell's equation. Maxwell's equation tells us how these things behave in terms of charges, and we also have the Lorentz force law, which tells us how charges are related to electromagnetic fields. We also know things about momentum. We know that momentum is, of course, another 4 vector, so it must be energy momentum. We know that things like Maxwell's equations are unchanged for all choices of gauge. So we have complete freedom over this extra field that we add. All we have to do is take a completely arbitrary field. If we take the derivative of it, we can add it to our electromagnetic fields without changing Maxwell's equation or our forces or anything. We can actually use that freedom in something called the Lorenz gauge. This is not Lorentz, this is Lorenz. I've done that correctly. You can force that to be 0. You can force that to be 0 just by adding appropriate fields here. In which case, Maxwell's equation just looks like, which is obviously a lot more elegant. I should point out that this operator here often has another symbol and another name. It's also known as the D'Alembert operator. So our big lesson in special relativity is that space and time are linked. They're linked because as we change between inertial reference frames, they seem to change one into the other. And so we really can't have physical laws that treat them very differently. So if you have physical laws that just have space treated on a different footing to time, you know to be suspicious of them. We always want to see space-time crop up naturally. And indeed, it's only in low velocity limits that we can pull out the non-relativistic forms of things. Okay, what else have we learned? We've also learned that at the very heart of physics is this thing called action. Action and the Lagrangian dominated our discussion in classical mechanics. And we discovered that if we could write the action for a large number of coordinates and their derivatives, then we ended up following the principle of least action, and therefore we'd have the Euler-Lagrange equation, which would be a set of ordinary differential equations for each of our variables. For fields, particularly relativistic fields, we discovered we needed to talk about the Lagrangian density, which was a function of the fields and their derivatives, and again we'd end up with Euler-Lagrange equations, which would really be one partial differential equation for each coordinate we have for our tensors. So this is for a 4 vector. If we had more indices, we would simply have more of these as we'd have more indices in there, and we sum over the derivatives there. So our Lagrangian density has to be constructed in terms of scalars, so it's coordinate independent, and then this integral over space-time volume is coordinate independent, and so the action becomes coordinate independent, so that's just a scalar, and therefore these equations are safe tensor equations. And we can see that by eye now, whereas over here, if we look at that with our special relativity trained eyes, we cringe a little. We say, oh, look, there's a time derivative, and oh, there's coordinates being treated differently. I wonder if that's even safe. I wonder if that could possibly be true. In fact, this is not the first time that we tried to get a Lagrangian for fields. You may recall that earlier we came up with a Lagrangian for a single charged particle in an electromagnetic field. And it's not very clear that this is Lorentz invariant, and in fact it's clearly not in terms of scalars. This is particularly unlikely to be relativistic because that's the pre-relativistic kinetic energy rather than total energy. And we have there something that might turn into 4 vector forms. Let's have a go. So this term is kind of easiest. So we've got a charge, and we've got the scalar potential and the vector potential. And so put together, that's obviously going to be something like the 4 vector potential. And we're contracting with the velocity. So we'll try the 4 velocity. And so we've nearly got there, except that we're integrating over time, which is frame dependent. So we'll integrate over some kind of scalar that will get to the right limit, indeed the proper time. Okay, now what about this term? Now this term is the kinetic energy, which is an extremely frame-dependent thing. You can move into a frame where the kinetic energy is 0. So why don't we choose something else like the total energy? E equals mc squared, that's the scalar. First inspection suggests that that's too simple because it doesn't depend on anything, and so it's not going to lead us to any dynamics. But in fact there is hidden dynamics in there because it's depending on the proper time. And the proper time in a particular coordinate frame is going to depend on the coordinates. And indeed, if we look at that and we take the expansion, we find that we need a minus sign there in order to get the kinetic energy term in the low velocity limit, along with an offset. And so that, in fact, is a relativistic version of this, and you can see that it's almost the same. So this term actually came out quite naturally as a relativistic term, and again, electromagnetism behaves very well with special relativity. And this term just needed a little bit of a tweak in order to become a relativistic term. And this is an action that is manifestly Lorentz invariant.